And I'm doing this, I'm intentionally leaving this in this view because I want to be able to use different color pens when I'm doing some of this stuff as we move through. Okay, so that's why this isn't bigger. Is that anybody going to have an issue? You're able to see okay. Otherwise, you can come up and sit in the command center here. All right, so we were talking about water dissolving non-ionic substances, and we talked about how that water then, that substance would need to be polar. So when you have these hydroxyl groups here, these OH groups, that's always going to be polar. And this, I think, is where I was losing you yesterday. You guys were all like off in la la land packing up and everything. So remember, this has those lone pairs of electrons on it. And that's what they're drawing here, is showing you that those lone pairs of electrons are going to orient such that the positive ends are going to connect with this hydrogen. Okay, and that's how the water will end up surrounding that material. This is the acetic acid. Sometimes you will see that written as this, but, and then it will have a minus charge there for the acid. Then would have a hydrogen over here, and that's what your acetic acid looks like. When they draw it out like this, they're really trying to give you a hint that this is going to have one of those, be able to be a polar bond. Okay, it's got hydrogen bonding. Does that make sense? Okay. And then you've just got to make sure that you bring those around. Okay, so 3 steps have to occur in order for a solution to form. The solute particle has to separate. That requires energy. The solvent particles have to separate. That requires energy. And then when they come back together, they're going to release energy. So if this process here has more energy than these two, these have less than this, then you're going to have an exothermic reaction. Energy is going to be given off to the environment. And that is what we were talking about, I think, the other day when we were talking about diluting down acids. This process here where they come together is extremely exothermic. It's going to give off a lot of energy. Okay. The amount of energy needed then depends on the materials that you're working with. Polar substances will dissolve into polar substances, and nonpolar substances will dissolve into nonpolar substances. That comes down to the red rover. Okay, we've talked about red rover. Okay, if these nonpolar substances come around to a polar substance, the polar substance is going to be attracted so well that they're not going to let a nonpolar substance in that doesn't have a charge. This attraction between these positives and negatives is going to be so strong that it's not going to allow the nonpolar in. Okay. When you're working with polar and polar, though, the attraction of the particles between here, so the attraction between the intermolecular forces between here and here, okay, are going to be, so this is one of your polar substances here. Okay. So let's just call this one our solute, like sodium chloride. Okay. So we're going to pretend that that's sodium chloride. There's attractions between these ions. Everybody buy that? That's why they stay together. We also end up with a solvent particle. So we're going to call that one, that's water. This is your water molecule. Let's just do one more water molecule here. Okay, there is an attraction between these, right? We've got hydrogen bonding, we've got dipole, and we have London dispersion forces. So when these come together, the attraction between this negative here and this hydrogen is going to be greater. This negative is going to want to go over here to be with that hydrogen more than it wants to stay with this positive ion. And this oxygen is going to want that sodium or that chlorine to come over more than it wants to stay together with this other water. Does that make sense? You can end up with some substances, though, like silver chloride, where this is not the case. The attraction here is going to be stronger, and the attraction here between these is going to be stronger, and that's why sodium chloride is not soluble in water. It won't mix with water. It'll just right to the bottom. You end up with a couple different situations then in terms of solubility. If we run out of solute particles first and still have solvent left over, then you have something called an unsaturated solution. Because you still got solvent particles. If we added more salt into that, we added more sodium chloride into it, okay, you'd be able to mix it in still. So that's called unsaturated. You can also end up with a situation where you have this has been all used up. All the water has been used up, and you've got extra solute. And that's where it's going to settle to the bottom. It can't mix in. It doesn't have any more water to be able to surround any more ions. And that situation is called saturated. Okay. All right. So hexane. Is hexane polar or nonpolar? Here's the formula for hexane.
Nonpolar.
Nonpolar. Okay. You're just going to have C's repeated all the way down with H's attached to it, each C. Good? I'm not going to bother to draw it out. You know that water is polar. So this is nonpolar. This is polar. So we need to determine what these are. Sodium chloride. Type of IMFs. LDF all day. Yeah. We'll just do a line down here for that. It's actually, this doesn't have dipoles. This is just ions. So it's ionic. Okay. Now, when it gets together with the water, okay. Oh, I guess we had to put down what this is. Missed that part. Dipole, and H bonding. Okay. When it gets together with water, then it's going to form an ion dipole. Because you're going to have the ion, such as Na, so that is going to be a positive charge, and then I'm going to have my dipole of my water coming in, so that's an ion dipole attraction, and that's going to be with water. All right, what is C3H8? Polar or nonpolar?
Nonpolar.
So is it going to mix with hexane or water?
Hexane.
Hexane, yeah. So that's a check. CO2. It's nonpolar. But what do you know about CO2? It mixes with water. Yeah. Why in the world? I actually had to go and talk to Mr. Schramm about this one because I was like kind of blown away by it. Even though it's nonpolar, you're still going to have an attraction for these oxygens because they're both electronegative, very electronegative. The electronegativity difference between the carbon and the oxygen is great enough that you're still going to get some attraction in water. So it is going to mix in water just to kind of.
Would it mix in both, or would it only be water?
I don't know. See if Mr. Schramm's over there, Nicholas. Of course not. Okay, we'll come back to that. How's that sound? I'll get you an answer.
Is he experimenting?
Yeah. See. Okay, so this is going to be double bonded to the oxygen, and then we're going to have a hydrogen here and a hydrogen here, I believe. Okay, so I had 4, 6, and 6 is 12. 2, 4, 6, 8, 10, 12. Okay, so everything has a full octet. We're good. Okay, so we don't have, I'm not sure about this one. Starting to question everything in life, you guys. Oh, it does say in my notes that it dissolves better in hexane. So it must dissolve in both. So we've answered that. And then this one is going to have the same idea where it's going to end up dissolving well in water. So even though it does dissolve well in, we'll do this and this. How's that sound for the CO2? Evelyn's about ready to kill me. She's very happy that she has an eraser on her writing device that works. She's about ready to kill Lippy. All right, the we do you're going to do on your own. We got to move. All right, this is a rehash of chapter 5 from last year. Okay, we have spectroscopy. You're actually going to be using this this week. We have where we're going to be looking at wavelengths, and that's what your lab is going to start you out tomorrow, and then you're going to continue on into Monday for it. Okay, and I think I've got it scheduled for Tuesday of next week too. So remember, you've got your UV light here. Be careful with these diagrams because you will oftentimes see them flipped, where you have the radio waves over on this side and the gamma waves over here. Okay, so just kind of when you get to them, make sure that you look and see which way they've got the number line going. Does that make sense? The gamma rays then are going to be the ones, and UV and X-ray. All of these are called ionizing radiation because they can kind of play with a lot of different things in your body and mess you up. Okay, that's what causes your cancers and stuff like that. The UV will do it less than X-rays, and X-rays will do it less than gamma rays. Okay, this is hard to avoid entirely. Okay, unless you're like a vampire that never comes out during the day. But other than that, it's hard to. But our bodies can handle some of it. Okay, they get a little angry with us sometimes, like with our sunburns. Okay. But these things can affect you. The X-rays and gamma rays can actually affect you very similarly, except you need much, much less of it to make it happen. Okay. Moving the other direction then, light, we're okay with that. I told you my sleeve was that. Infrared then is heat. So that's heat energy. You're familiar with microwaves. You got your microwave ovens. Your cell phones work with these. And then radio waves. They still use them. I mean, that's how when we have our walkie-talkies here in school, they're coming across that way. Police use them all the time. You may still have one in your car that you use occasionally, but a lot of us just do our podcasts from our phones or whatever and hook our phones in, and then that would use microwaves. Okay. The difference between these is the wavelength. And then if we shorten the wavelength up, we're going to increase the frequency. So it's like here where, you're getting hit very slowly by these waves and it doesn't do any harm. But you move up into this region and you are getting pummeled. Okay? And that's why your body can't handle it. It's getting too much energy in too short a period of time that your body can't deal with it. And then you end up with bad things like sunburns and cancer and da-da-da-da. All right. Molecular movement then. Molecules move different ways when they're exposed to this radiation. Okay? You can have bending of the molecule. You can have it stretch. Hi, welcome back.
Hi.
Were you on some tropical beach?
Yeah,
Someplace
I
good?
was.
Okay, good. I'm sorry to bring you back to this world. Asymmetric stretching, where they're like getting, pulled different ways. We can have, and this is, are you going to pop me over? Are you going to let me move this? Oh, you're going to let me move it. How nice today. Maybe you will. There we go. You can have rotational movement, where it rotates. And then you can have transitional movement, where it completely moves from one place to another. Okay? So different molecules act in different ways. Okay. So this is what you need to know. Microwaves have rotational movement. Okay? How do you remember this? You have a microwave oven, right? What does the thing do in the microwave oven? It rotates. Okay? So if you can remember that your microwave rotates your food around, then you can remember what the microwave does to molecules, these microwaves, right? So rotational movement. Infrared is going to be vibrational movement. What happens if you take your hands and you vibrate them back and forth together? And what is infrared radiation? Heat. Okay, so you're generating infrared when you do this. You're vibrating your hands back and forth, and that's causing heat. And that's infrared. So can you remember that one? Okay. Light, UV, everything from light above is going to cause transitions. Cause those electrons to jump. And we learned about those jumpings last year, or whenever you had chem, because remember, the electrons climb up levels, and then they fall back down. Okay? So just remember Lippy falling off a ladder. She's transitioning back down. She's unstable. Okay? So again, UV and visible light are going to cause these things to transition. They're going to transition those electrons. Now, we can take advantage of some of that stuff with these spectroscopy devices. Okay. Did you guys get the volumetric flasks out? It's on the list. Check the list to make sure you get everything out. Yep, that's it. Yep. Okay. So in the little cardboard boxes back there that they've got pulled out, you've got a spectroscopy device. Okay. It's turned upside down, I think. Yeah, there you go. And then you're going to have these little cuvettes. that will fit down in to those spectroscopy devices after you've cleaned them properly with your chem wipes, which I'm going to show you how to do tomorrow. Okay, so that is how they're going to work. And what happens is these spectrophotometers are going to look at the amount of light that's absorbed, and then from that, they know how much light they're sending out. They can subtract that and tell you how much is absorbed and how much is emitted and absorbed by the sample, transmitted. Okay. Why is this not moving? Because I moved the thing again. Okay. All right. 2 samples of copper to sulfate are analyzed with visible light. One absorbs twice as much light as the other. What does that tell you about the concentrations? Yep.
Absorb more light, have a higher concentration.
Right. So if you think about this, if you have your copper sulfate, which you guys are going to have copper nitrate tomorrow, if we have more copper nitrate, and you have to have something that has a color, okay? So this is going to have that blue color, pretty blue color. If you've got something that is twice as, I should make those amounts the same. So this is twice as concentrated as this. When I shine light through this one, so I'm shining light through here, some of it is going to get absorbed by those particles, and then some of it's going to come through. I don't want 4, though. I only want 3. Okay? Now, if I do the same thing with this guy, I shine the same light through here. So I got 4 rays of light coming through. Because this is more concentrated, more of that light is going to get absorbed by those particles, and less of it's going to come through. Does that make sense? Remember the copper sulfate that we had? We did a whole kind of spectrum of it. Okay, that's the same idea as this, and that's what you're going to be doing tomorrow in lab. Is you're going to be doing your calculations, and then you're going to determine how much you need to dilute it down to get different concentrations of this. So what must be true of the solutions to get this result? They have to have a color associated with them. They have to have a pigment. Okay. What type of changes occur within the molecules in the process of this? That's going to be transitioned. Okay. Good. All right. Let's see if I can get through this. Okay, photoelectric effect. Again, the we-dos are on you. You've got until the 25th to get them done. So, yeah. The rest of this packet.
Just a little bit.
No, 25th. See the board. Tomorrow, I'd like to have the pre-lab done if I can get that far. Okay.
What are we doing next Monday?
Your lab was like,
What?
What are we doing next Monday?
Monday, you're still working on your lab. Tuesday, you're still working on your lab. Wednesday, you're going to have a work day
Does that mean it's a
for
hard lab?
your pre-check or progress check. What?
Does that mean it's a hard lab?
It's not hard. It's just
Time consuming.
to make up all the mixtures. You're having to dilute down all these different mixtures and everything. So it takes, it's a process. All right. So when light strikes materials, they can cause electrons to bounce off. This is called the photoelectric effect. This is how the solar cells work. It's how your solar calculators work, if you have a solar calculator. So it's how those charges work. So a certain amount or a certain frequency of light has to hit these in order for that to happen. If that light doesn't have that frequency, it just hits it and just nothing happens. Okay? But if it gets the right frequency or higher hitting it, then those electrons will pop off. They can capture those electrons, and then that's your electricity. That's how they run different things. Okay? All right. Like I said, certain frequencies of light will hit and nothing happens. So red has less energy than violet. How do you remember that red has less energy? Because infrared, if you go back to this chart here, okay, infrared is down here. Notice the word red, okay? And you can always remember that violet is over here because that's what's going to cause damage for you. Okay, so that's how you can remember the orientation of this rainbow. Does that make sense? Okay. All right, so if we hit it with the right frequency, we can cause electrons to pop off. If we hit it with a higher frequency, it's going to cause those electrons to pop off even harder. Does that make sense? Because it's got more energy associated with it. It's kind of like me pushing my coffee cup like this with a little energy. I have to have a certain amount of energy to get it to move, right? I can just have that amount of energy, or I can give it a lot more, and it's going to move a lot faster. It's the same idea with these electrons, okay? So on a bright sunny day where we got lots of sun coming in, you're going to get a lot of electrons popping off. A real cloudy day, it's not going to work so well. That's why like solar energy has not taken off as well up here in Wisconsin compared to like down in Arizona, okay? Because our winters are like kind of the way it is today. They're just cloudy and gloomy. I mean, we can go days and days and days without seeing the sun here, okay? We also have shorter days, okay? During the summer, we have longer days, but during the winter, they're very short. So if you're going off of solar for your only source of electricity, it's not going to go well, especially in the winter when we only have like 8 hours of daylight, right? And there's days that we come to school in the dark and we go home in the dark, okay? So not always the best thing for this part of the country. Now, they're getting better with it and they are starting to install some stuff, but again, it's not, if you have your choice of Arizona or Wisconsin to put solar in, go with the Arizona, okay? Yep. So amount of energy needed to eject an electron is thought in terms of the longest wavelength, the less frequent, that would still eject that. Okay, so that gives you a threshold. So here's just kind of a diagram of that. And then we talked about this guy. This is one of your equations that's on your equation sheet, okay? Or two actually. So here's one of your equations. Energy equals Planck's constant. They give you that constant. You do not need to memorize it. Times the frequency. And then we also have speed of light equals frequency times wavelength. And then we can combine, we can do a mashup of those two equations and get this guy. Because if we rearrange this one so that frequency equals C over wavelength, then we can just substitute this for this and end up with that. Yay or nay?
Yay.
You rearrange this equation so that speed of light divided by wavelength gives you frequency. Everybody go with the algebra there? And then in this equation, I had frequency. So if I just take this and replace this guy, I've got this equation over here. Better? Chase is in La La Land. Okay. So they can actually determine what kind of material will work best for this. And that's what that slide's about. All right. So energy of photons must meet a minimum energy. Just like I said with my coffee cup, I have to meet, I can press against it and not anything happens. I have to meet a certain amount to overcome the friction of the table. Oh, that was almost physicsy, wasn't it? I'm sorry, you guys. And then the shorter wavelengths are going to have more energy associated with them because they're going to hit more frequently. The rate of emissions then is known as photoelectric current. It's going to be proportional to the intensity of the light. So the more photoelectrons you get, the more intense it is. Dim light bulb versus a bright one. And then if the minimum energy is met to eject those, then you can actually determine the kinetic energy of it. Again, physicsy. This is back when we had to do mental math. We don't have to do that anymore. Thank you, God. Metrics, then, you need to be able to know like mega and kilo. These are usually the ones that show up on there. And then you also need to know nano, okay, and these conversion factors. So for every one of these, I have 1 times 10 to the negative 9th of these, or 1 times 10 to the 9th of these. And for every one of these, I have, or for every one of these, I have 1 times 10 to the 3rd. And then vice versa. So metrics. All right. So, honestly, I think you guys can probably do these at home. So we're going to come back together and talk about these with questions you have on this one. Tomorrow, I'm going to begin the lecture with this. We're going to talk about the Beer-Lambert law. Then I am going to react the brass pellets that I have with nitric acid and show you how we're going to create our unknown. And then you guys are going to start crunching numbers and try to figure out how you're going to put things together and create your solutions. Okay. There will be 7 lab groups tomorrow instead of 9. I know you're disappointed that some of you are going to have to work in groups of 3. I only have 7 of the photo spectrometers. So what's due tomorrow? There is a pre-lab for this. You know, honestly, let's just push that off to Monday but if you're like got a little extra time tonight, you might want to work on some of those other ones so you don't have so much this weekend. Okay. But that's completely up to you.